Greetings, students from Stonehill International School. My name is Dr. Richard Clark. I'm a professor emeritus from Millersville University of Pennsylvania, USA. I retired in 2022 to take on the role of president of the American Meteorological Society, and I still serve in that role as past president of that society. While I was at Millersville University, my primary role was to teach courses in thermodynamics and chemistry of the atmosphere and boundary layers and turbulence. And most of my research that I've done over the years, which has been mainly airborne and balloon-borne type research, has focused on boundary layers and turbulence and air chemistry. It gives me great pleasure to serve again as a judge for the Stonehill High School Science Bowl. I'm really looking forward to seeing the final presentations, and as part of this modern problems require modern solutions. And I'm sure that there is no shortage, by the way, of modern solutions that are being identified to tackle some of these wicked problems that we see around the world. And weather is one. Some of you may have heard of the butterfly effect, where a small perturbation in the atmosphere can cause a change in the weather downstream. These are the kinds of things that concern us, because this is what introduces uncertainty into our weather prediction. One of the things that you're going to be looking at are some of the challenges, and I'll speak to those in a second, but some of the challenges that are associated with weather prediction, both in India and around the world. Those challenges are mostly associated with how to either minimize the uncertainty and quantify the uncertainty. And then once quantified, issue a degree of confidence that one has in a weather forecast. This can be done in a number of ways. One is, and probably the most predominant one, is through ensemble modeling, where you don't trust just one model. These models are deterministic for the most part, and you don't just trust one model to make that prediction. You trust as many models as you can, you sort of get your hands on, and you do some type of statistical distribution on their output. Like, for instance, let's suppose you're trying to predict what the geopotential height is of a 500 millibar surface. You're not going to just rely on a single weather research and forecasting model, what they call the WRF model. You might look at the Global Forecasting Systems model, the GFS, or the European model, or the African Met Society model, or whatever, as it applies to that particular region, and look at not just how the models perform and do it. It's not just simply taking a Gaussian kind of distribution and doing the average. It's looking at what models do you have confidence in? What models have done really well in the last 3 or 4 days, and gives you more confidence that in the next couple of days they're going to be doing an adequate job. There's a real difference between weather and climate, by the way. And while we're on this subject, weather is something that is going on now. It's what you're able to predict in the near future. Deterministic models will do a relatively decent job of forecasting the weather. Obviously, the uncertainty grows with time, but they do a fairly decent job of forecasting the weather out to about 2 weeks, and even in some cases out to a month, if there's good signals out there from which they can assimilate the data and produce predictions. But beyond that, the uncertainty becomes so large that you really can't trust deterministic models. Now, this is being enhanced by generative artificial intelligence. I mean, artificial intelligence is the next big step in improving weather forecasts, because it's going to be able to take this copious amounts of data that's generated worldwide and feed those into models and then learn from that data as to what mistakes were made. And you know how it is. The more mistakes you make, the better it is for the learning algorithm. And so if mistakes are made, those mistakes can be corrected by generative AI built into these models. So we're looking over the next 3 to 5 years, short term, a very significant improvement in weather forecasting due to the generative AI being incorporated into the weather forecast. Another thing that's coming down the pike, but it might be a little bit further off in terms of how it affects meteorology and climate science, is quantum computing. We, as the image behind me shows, we're dealing with a global environment, a coupled atmosphere ocean system, sun-driven energy. 99% of the energy that comes to that drives the atmosphere and the ocean comes from the sun. And so the atmospheric systems that you see behind me, it requires significant computer power. And if we can bring quantum computing into that mix, we're going to be able to run many, many more ensembles and get greater confidence and quantitative uncertainty in those models. So those are the kinds of things that we're going to be looking at. Climate, on the other hand, is the average of weather. It's the things like melting of the Arctic ice sheets, sea level rises, and things like that. Human-induced climate change. Okay? Humans are the primary reason for the climate change that we're seeing in this current epoch. And so that's all related. We're not going to be dealing with climate in this exercise. It's going to be primarily focused on weather prediction and the challenges of weather prediction. Some of those challenges, as they may relate to you, but not necessarily only to India, would be high variability in monsoonal patterns. If there's a difference in the El Nino, or ENSO, it should be called El Nino in Southern Oscillation, that can have significant impacts on the variability of the monsoon, sometimes even cutting off the monsoonal circulation entirely and causing drought when otherwise there would be significant rainfall. Other challenges might be there's complex terrain and regional that affects regional weather patterns. It's very different. The weather that you experience in a coastal environment is very different than the weather you experience in the mountains. And models typically have a difficult time whenever it's a very convoluted mountain range. So that's something else that you might be able to look at through this process of this challenge that you're confronted with. Limited observational data in remote areas. Now, this is becoming less and less a challenge because currently we're able to put out remote instrumentation that's driven off of solar panels and puts data into the cloud via satellite or cell phone towers. And we can put these out, they're fairly cost efficient, and you can put a lot of them out and get a better network of data. But the data is so important because the data is what's used that is assimilated into the model that forms the initial state from which the model begins. If you're going to predict the weather, say out 3 days, you have to start with the best possible initial conditions, the least error in the initial conditions before you before you start the model and run it out 3 days, 5 days, 7 days, 2 weeks. And like I said earlier, with increasing time comes increasing uncertainty and greater error in your output. So the more data that you can assimilate into that model, the better off will be your initial condition and the better off will be your resulting model predictions. Rapidly changing climate patterns is, like I said, there's a big difference between weather and climate, but in some places where you have these microclimates that are capable of changing, like for instance, flash droughts are becoming a very interesting topic of research these days, where a drought will occur over a period of a month or two, but through positive feedback mechanisms, it will lead to droughts. It will lead to more significant droughts that actually will become more climatological features than weather features. We see this in various regions of the American Southwest and in the Sahel region of Africa. A cyclone path prediction. As climate changes, as weather patterns change, as a result of that, the path of cyclones can change, and places not experiencing cyclones can experience cyclones, or cyclones can stall, as they did recently over India, and produce rain in areas that weren't expecting rain, and dry conditions in areas that were expecting increased precipitation. And then finally, another challenge would be, say, the urban heat island and microclimates. You can have these extensive high pressure systems setting up over a region that can lead to, 30, 32, 35, 37 degrees Celsius temperatures over long periods of time. And as you know, there's something called a wet bulb temperature that is related to your body temperature, that if you cannot get rid of sweat, if your sweat does not evaporate coming off your body, then your body cannot cool. So temperatures like 30, a wet bulb temperature, that's what they call the temperature where water would be evaporating. That temperature, if it's 37 degrees, your body's not able to get rid of the heat by sweating, and that can be disastrous. That is a significant health-related issue there. So weather predictions are made using numerical models that are written in Fortran, C, Python, the programming languages that some of you probably already have. And these are gridded models that assimilate data in and run it out as far as as necessary for in operational. Like, for instance, if we're doing U.S. operational weather forecasts, we run it out, we get weather forecasts every hour out to 10 days, which is typical. Beyond that, it becomes a little bit of a statistical nuance that you have to play into the model. Already mentioned the key challenges. Another thing that we want to ensure on a global scale is that the challenges that we face and the solutions that we find to these wicked problems are aligned with the UN sustainability program, and that is, for instance, zero hunger. Whenever there are weather catastrophes, mudslides, flooding, the normal needs of the population cannot be met. Clean water and sanitation. There's flooding. The amount of pollutants and chemical pollutants that get into the water as a consequence of flooding, that should be fairly straightforward. Clean energy, affordable energy. Industry and infrastructure, and infrastructure can be significantly affected by the 1,000-year flood or the 500-year flood. Sustainability in cities, urban heat islands, things like that. These are all part of these UN sustainability goals, climate action, life on land, and partnerships with other communities to ensure that there is a free flow of information and data, so that we can all sort of share in the knowledge quotient that is available to us. So I'll stop there. I wish you well. I look forward to seeing the top 5 finalist presentations. There's plenty to talk about. These are wicked problems. Some of the challenges, as I mentioned before, can be influenced by AI, improved by AI and quantum computing. But there's other challenges, like there will always be uncertainty in weather forecasts. So the bottom line is, how can we reduce that uncertainty? How can we build better confidence in weather forecasts so that we can relate that to the public, and they can respond. That is for their own decision making, and they can respond accordingly. So I wish you well. It's a pleasure to be here again, and I'll sign off now. Thank you. Bye.